Good morning. How are you? Good morning.
You are now unmuted.
Can you hear me? Okay, that's good. Starting now. I'm so sorry. I was caught up in something. 10 minutes gone. So we are
Now
starting
muted.
today with this chapter, which we call it Kelvin's Economy Law. Is everyone in? Not all. Many people are not attending. Anyway, before we start, just to mention, last week we discussed about the power generation and we call it power conversion from other sources of energy, and then we went to discuss a little bit about transmission and distribution systems. But more will come as we will come across the chapter. So this chapter, Kelvin's Economy Law, is mainly related to three different types of activities in power systems. When I talk about three different types of activities in power system, as I mentioned the last 2 weeks, that in power system with a huge power system, it's a nationwide power system. Sometimes it goes beyond the boundary, meaning international power systems, because we connect our power system to another power system, either to supply power to them or to buy some power to meet the demand of a particular nation or a country. So a lot of activities. Now we also classify them in many different ways. Like for this one is related to power system planning, power system design, and power system economy. So all these three, power system planning, power system design, and power system economy, is related to this chapter. So planning means what? We need to plan. For example, we are sitting in now in 2020. If we are sitting in 2020, we must know what will be the scenario in 2050 in the country of South Africa or even in any other country. Actually, each and every country should plan for 2050 now, because it takes time to implement that system. It's not like other commodities or other equipment that we can procure, meaning we go to the store or we order them online or offline, and then the equipment will be delivered, and then we can just plug and start playing with that. No, it doesn't happen like that. It takes a lot of time in terms of planning and implementing, commissioning, and operating them in a desired manner. So that's the part. So when we come to this Kelvin Economy Law, that's the part of the planning. And I discussed this thing, generation of electric power and all those stuffs last week. I'm coming to this chapter now. Now, as I mentioned, that it's related to power system planning, and it's related to power system design, and it's related to power system economy. So I'm coming to this design. Now, when we have power system, mainly what comes into our mind, those lines, conductors that carries current or that carries power, or power flows through those conductors or the lines. That's what we think in the first place. So when we have power line, meaning we said that in generating stations, we have a number of generators. They are operating in parallel, and from those generators, we connect a step-up transformer to increase the voltage level to a very high level to reduce the current, hence to reduce the power losses that might occur in the transmission lines. Now the power is on the transmission lines. From the transmission lines, it goes to the distribution system, where there will be a number of substations involved. Those substations will take down the voltage according to the requirement to reach different types of consumers' premises. It can be industrial, it can be domestic, it can be commercial, and so on. So as we think of those lines, transmission lines, distribution lines, we need to think or find, when we put a line, transmission line, meaning it has a conductor that will be capable of carrying that current. So we need to know that current. So if we don't know that current, then we cannot design a power line. There are many things that need to be considered when we design a power line, but in this chapter, we are focusing on the dimension, meaning either the diameter of the power line conductor or the cross-sectional area of the conductor. Now, when we're talking about that, many other things, many other factors come in the scenario. Like if I buy a conductor, that conductor will be having a certain diameter or a cross-sectional area. According to that diameter or cross-sectional area, that conductor will be capable of carrying a certain amount of current or power. So once that is happening, other things are also happening. Those are the several factors. The first thing that comes into our picture is that what we talked about, the power loss will take place in the conductor. So when power loss takes place in the conductor, how we know the power loss? If we know the current that is flowing at any moment of time or in a given period of time, which is going to be constant. If we consider it constant, if it varies, then it varies. So the power loss. Together with the current, we need to know the resistance of the conductor. Right? So when we have resistance for the conductor, we know the current, we can calculate the power loss. Now that power loss is thought as a loss. The reason is that that power is not going to be delivered to the consumer. And if we go back to the generating station, we had to spend money and time was used, human resources were used, operational engineers were used to convert other forms of power to electrical power, and then we're losing it here in the transmission line, we're losing in them distribution lines, so we're losing them. So we cannot afford to lose much, but obviously there will be some losses. So that's the one factor. The second factor is when we buy a conductor of a particular diameter or a cross-sectional area, we pay accordingly. If I buy a smaller diameter conductor, then I pay less. If I buy a larger diameter conductor, I pay more because of the material cost. It may be of a copper conductor, maybe of an aluminum conductor, it can be of a mixed material. There are other materials that we use in combination with copper and aluminum. So these several factors are coming. So those are the things that we are talking about. Now the economy, I said power system planning, power system design, and economy. Now economy is also the heart of this chapter. When we're buying a conductor, we're paying, so how much we can pay? Can we put a very large diameter conductor that will be capable of carrying a large amount of current, but in an actual practice in real life, that amount of current is not going to flow through the line in any time of the year, or in 5 years, or in 10 years, or in 20 years time, like I was saying, that we are sitting in 2020, I'm planning for 2050. So I'm going to put a conductor line that is going to carry a certain amount. I want to be safe, for example. I don't want to find people in 2050 that what I designed, that conductor is not capable of carrying that amount of current. So I want to put a very large diameter conductor to ensure that that doesn't happen. But what I'm doing in that process, I'm spending a lot of money. So where that money is going to come from? Money doesn't come from that organization. For example, if we are in South Africa, we talk about Eskom or Ethekwini Electricity or other Ekurhuleni Electricity or Mpumalanga Electricity, whatever. But it does not come from that organization. Those organizations usually at the beginning, they used to take loans from various financial organizations, and then they pay the principal and also the interest. Now that principal and interest will come again, not from the electricity organization. It's never going to come from Eskom, it's never going to come from Ethekwini Electricity, as for example. It will come from who? It will come from the consumers, meaning each and every consumer, irrespective of what type of consumer they are, domestic, commercial, agricultural, or industrial. Each and every one will pay that amount proportionally. So that's why we need to make sure that we trade off carefully here when we're choosing the diameter of the conductor and so on. So that's where that economy lies. And the cost of conductor is a factor here. So how much we are spending in the conductor as a material cost. And then we come to something like the most economic size of conductor. The main aim of this planning and design, considering the factors like power losses taking place in it, the amount of current of power that should be flowing through the conductor, then we try to find out the most economic size of the conductor, meaning I don't want to buy a very small diameter conductor, I don't want to buy a very large diameter conductor, but what should be the actual cost of conductor? We should economize the whole system of operation, and we try to find out how will be the total annual cost. Now, when you're choosing this most economic size of the conductor, like I was mentioning, I'm thinking about 2050. But when we think about economic size of conductor, we look at the total annual cost of the conductor. Now, that annual cost comes from two different factors. One is from the loss taking place in the conductor while it is carrying any current or power. And the second one comes from the cost of the conductor. But cost of the conductor does not come directly. It comes from that principal and interest. And also, there is another thing that you need to consider is the depreciation of the conductor. Like I'm putting a conductor today in 2020, it will be in operation for 30 years. Up until 2050, I will put a new one after 30 years. So over 30 years, I'm paying that interest. So that interest and depreciation things come into the picture as well. Is that clear?
You are now unmuted.
Do you have any questions? Ask question. What questions you have in
You are now muted.
regard to what I just talked about? Ask questions. What questions do you have? Okay, don't have question. You write questions if you can't speak. I see the microphones are off, but you must write down the questions. Now, when we come about the annual cost, like in the previous slide, you remember that we talked about the most economic size of the conductor, and the most economic size of the conductor is related to the total annual cost that we spend on the conductor. So that annual cost is now divided into these things. The fixed standing charges, meaning there are some costs that are fixed, constant, and there are some charges that are running charges, meaning it will depend on the operation, how we operate that line. If the current is flowing through the line, then there will be some charges happening in it. If there is no current, nothing. If more current, more cost, and things like that. And the cost of interest and depreciation, and also sometimes we do some maintenance. Initially, this maintenance part was not considered in Kelvin's law, but later on it came into the scenario. And then we also need to know the cost of electrical energy, because when we have converted other forms of energy into electrical energy at the generating stations, so we spend some money in that process of conversion from other sources of energy to electrical energy. So some cost is incurred in that process. Now, when we come to the transmission line and hence to distribution system in the following step, what happens? We put more and more equipment, we put more and more controls, we put human beings, operators, engineers to operate that line, meaning we're spending more money. So costs involved in that. So if we cannot transmit the power or energy produced at the generating stations to the consumers, we make a loss in between. Now, the cost of electrical energy is always very important. How we can minimize it or economize it so that everybody can have access to it or they can afford to it. So those costs and other factors are coming into the scenario. The first one is the fixed charge or the standing charges, and that fixed charge or standing charge is related to the size of the conductor in general. When we talk about the size of the conductor, meaning we thinking about the diameter or the cross-sectional area of the conductor. So size of the conductor means is the cross-sectional area of the conductor. The reason why we need to consider the cross-sectional area of the conductor is that larger the diameter of the conductor, larger current can flow through it. Right, the larger the diameter of the conductor, the larger current is allowed to flow through the conductor. So when we talk about the charges now and relating it to the diameter of the cross-sectional area of the conductor, we can represent that according to Kelvin's law that was stated in 1881. So you can imagine, so it was about 140 years ago. It says that if you use a larger diameter conductor, you spend more money, meaning your cost of conductor is directly proportional to the cross-sectional area of the conductor, which is cross-sectional area of conductor is small a, and the cost of conductor is C1. So the fixed or standing charge is directly proportional to the cost of conductor. So that is C1, the fixed or the standing charge is directly proportional to C1, and that is represented as K1 times A. Now for the other charge, which is running charge, and running charge is related to the power loss. We don't consider the power loss. What we consider is the energy loss, because we pay in terms of energy. If you remember, on day one we discussed about how we pay our electricity bill. It's in kilowatt hour, so that's the energy. So we consider that running charges in terms of energy lost or energy wasted in the line during the operation for the whole year, meaning annually. So that is now related to the energy wasted. Now when we come to the energy wasted, the energy will come from power wasted or power lost in the line, whatever we say. So power loss, how we calculate it? We calculate it as I square R. So power loss is I square R, and when you want to get the energy, we will multiply it by the time, meaning T. So I squared RT. Now when we look at this equation, I square RT, time is constant, it's annual. So it will be a certain amount of a certain number of hours. So how many hours we have in a year? Yes, that's the correct answer. So 8760 hours in a year. 365 times 24. If you don't know or did not know, you must know that this is a very important number. That when you do the power system planning, design, and other related aspects, it will be utilized all the time. It's 760 hours, 8,760 hours. Now that part is solved. So we know that when we're considering the time, it will be 760 hours. Now we're coming to the resistance R. How do we know the resistance of a conductor that we have? How do we calculate, or how do we decide or determine the resistance of a conductor that is given to us? What are the things that we need to know when we need to find out the resistance of a conductor? What are the things you need to answer to determine how do you calculate resistance in those cross-sectional area? That's the one thing that is correct, good answer. And then what else we need to know to determine the resistance? Cross-sectional area and diameter, they are related. It's also correct. If you know the diameter, you can calculate the cross-sectional area. Constant of resistivity. It's not constant. Not called constant of resistivity. It's resistivity. Resistivity of the material that we used to make that conductor, and the length, that is correct. So we need to know three things: the resistivity of the conductor material, Is it copper? Is it aluminium? Or is it mixed? We call them homogeneous material or heterogeneous material. Homogeneous material means it's all of copper or all of aluminium. If we have a number of material mixed in it, it's composite. We can have aluminium mixed with something else, and so on. I will talk about that in another chapter. So we need to know these three things: the resistivity of the conductor material, the length of the conductor, and the cross-sectional area of the conductor. So if we look at this resistivity, we can't do anything. It's given. The conductor is already made of that particular material which has that constant of resistivity that is given. The length, we need that particular length. Like if I'm imagining that I need to put a line from Drakensberg to Durban CBD, we know that length. We can't do much there. So what is remaining now is the cross-sectional area. That is where we're coming back. So if we choose a larger cross-sectional area of the conductor, what will happen to the resistance? If we choose a larger cross-sectional area of given resistivity and given length, what will happen to its resistance R? It will decrease. But if we choose smaller cross-sectional area of the same length, of the same resistivity material, what will happen to the resistance? We choose, in contrast, if we choose a smaller cross-sectional area of conductor, what will happen to the resistance? It will increase, meaning we see that the power loss or the energy loss is inversely proportional to the cross-sectional area. We see the power loss of the energy loss inversely proportional to the cross-sectional area. So that's the C2, the running charge or the cost that we incur in the process of energy wastage in the line, whatever it is, distribution line or transmission line. That's the C2, and that is inversely proportional to the cross-sectional area of the conductor, which means K2 is the other constant, K2 over A. So the total cost comes from those two charges, fixed charge and the running charge. Fixed charge is directly proportional to the cross-sectional area, and the constant there is K1, and then we have K2 for other constant, and the energy loss is related here, which is inversely proportional to the cross-sectional area, because that is related to the resistance for a given current. Now we get the total cost C. Now from this equation, C is equal to K1 times A plus K2 over A, we can derive this situation that for the annual cost to be minimum, because we said we want the economy, and economy is achieved when the total cost is the minimum. Economy is achieved when the total cost is minimum. So when we have an equation, C is equal to K1 times A plus K2 over A, we can find out by doing that first order derivative, dC over dA. When you find it out, you can write dC over dA, meaning we taking the derivative of that equation. C is equal to K1A plus K2 over A, and then do the derivative where the variable here is cross-sectional area A. So dC over dA, what it will be? It will be K1, and that will be equal to 0. When you know that, when we want to find out the maximum minimum, we put that equation to be equal to 0. And then we will find that K1 should be, K1A should be equal to K2 over A, meaning C1 is equal to C2. It states now in a general statement that the fixed cost and the running cost should be equal for us to get the most economical cross-sectional area of the conductor while we're planning for designing a line. So that most economical cross-sectional area will be A. Is that clear?
You are now unmuted.
Okay, that's fine. And like I mentioned it earlier, that it was
You are now muted.
from long time ago, 1881, but after that some modifications have taken place. We'll discuss about that. Now, this small a is the cross-sectional area of the conductor that provides the economy in terms of the total annual cost being the minimum. Sometimes when we have this cross-sectional area and we know the current that the conductor is carrying, we can also sometimes find out the current density. Now, this density is not like those density that we come across in material science or applied mechanics or even in general physics. It's not that density, it's current density. It's the current that is flowing to a particular conductor cross-sectional of certain cross-sectional area, meaning the current per meter squared is the current density. So if we know the most economic cross-sectional area, then we can determine the most economic current density. So ampere per millimeter squared as well, we can determine, we look at that, because that current density actually tells us how much heat can be generated because of that power loss or the energy wasted in the line. And we need to make sure that we have an arrangement to ensure that the heat generated is dissipated into the ambient. Otherwise, what will happen if the heat generated in the conductor due to energy wastage or power loss, then the heat temperature of the conductor will start rising and rising and rising. At some point of time, the conductor material will start losing its properties and finally end up getting damaged, meaning burnt out or melt. That's what happens. That's what happens when we have an electrical short circuit or very excessive current flow through the conductors. So that's why we sometimes look at the current density as well. Let's go to the next one. But before I go, if you have any question, you can ask. Do you have any question on this previous slide? Any question? You don't have, so it's fine. Let's go to the next one. Now, in terms of the conductor cost, we saw that the conductor cost is directly proportional to the cross-sectional area of the conductor that we choose. And that is also directly proportional to the current that will be flowing or power that will be flowing through the line. So that's not that complicated. But when we come to this planning part of the conductor design, considering economy, standing charges, running charges, energy wasted in the line, the resistance of the conductor, and so on, we need to know the power losses that is taking place in the conductor, because we have to equate them. We saw that in the previous equation, we have to equate them. The standing charge is equal to the running charge. Standing charge comes from the conductor cost, interest and depreciation and all those. The running charge comes from the cost of energy that is wasted in the line annually. So we need to know the loss first. We need to know the loss first, then we can multiply it by the rate of energy, meaning how many rands per kilowatt hour. That's the rate of energy. Or tariff. The word that we use is the tariff. Now, to determine the losses, there are many things that we need to know. Now, the cost of power losses is the first thing. When we want to determine the cost of power losses, that is the first thing that comes into the scenario. Now, how do we know how much power will be lost? Is from that equation that I square R is the power loss, and then when we come to the energy loss, then we multiply it by the time for which that loss is taking place, energy loss. Now for us it's impossible, like the other day I was mentioning that the consumers of the users of electricity, they are switching on and off their loads or appliances as they need. So the current is always varying. Because of that variation, the power loss will also vary. That's why it's running. It's always variable. Now, for the electricity supply, they need to know how the load is varying, how the loads are being connected, how the loads are being switched off. They need to know. So what they do prediction. They do prediction, meaning they are plotting curves or making logs, writing down that now it's 11 o'clock, 11 a.m. in the morning, how many megawatts are being consumed by different types of consumers. 12 o'clock, noon, or how many megawatts? 1 o'clock, 2 o'clock in the afternoon, 3 o'clock, and so on. And they do it for the whole 24 hours. So if we put those values of megawatt on the y-axis and on the x-axis, if you put those hours from 12 noon to 12 midnight or 12 midnight to 12 noon, whatever way we like, it will give us a curve. We call it a load curve. Does it make sense? You need to say yes or no. So why others are not responding? I don't see many people are responding. You need to talk.
You are now muted.
So when we operate a power system, we always keep logs, meaning all the parameters, not only current, megawatt, or voltage, or frequency, everything is recorded. These days it's easy because we have even software that will generate the curve immediately online. So we create curves for all those hours, 12 o'clock midnight, 1 o'clock in the morning, and then coming back to 12 midnight. So 24 hours curve. It's called a load curve. And not only load curve is a very general word for this example that I gave, in which I mentioned that it starts, if you start at 12 midnight, and then you go to 1 o'clock in the morning, 2 o'clock in the morning, and then finally reach 12 midnight again, it's called daily load curve. It's called daily load curve. So it's daily load curve. The reason why it is daily load curve, because it's showing the loads for a particular day. Because it is showing the loads for a particular day. So that's why it's daily load curve. But sometimes when we do the power system planning, we need to go ahead of a day, like I was mentioning in the beginning, that I need to plan now for 2050. So it's years. So if you want to plot the megawatts consumed by the different types of consumers, we may plot it in terms of years. So year 2004, 2005, up until 2020. If I have a plot like that, then it's a very long term. So it's a long-term planning. That is the curve that I need for 2050 planning. But if I want to plan for next year, 2021, what I should do, I should look at what was the load or the consumption in 2020 January, in 2020 February, in 2020 March, April, May, June, July, August, September, October, November, and December. So if I put all those loads in the curve, we call it annual load curve, meaning it's showing the ER, showing the NM, the load generation or the power generation or the power consumption curve for a year. So it's annual load curve. So we got the daily load curve, annual load curve. But we also can be in between, meaning monthly load curve. We want to show the loads for a certain month for 30 days, day 1 to day 30. So that will be monthly load curve. We also can have a curve, seasonal load curve, like summertime, winter time, and other seasons. Because the load also varies from season to season. It does not only vary from time to time of a particular day. It doesn't only vary from 1 month to the other. It doesn't only vary from 2020 to 2050 because of number of population, number of connections, and the consumer premises. also varies from season to season. Summertime, people will put lot of air conditioners. Winter time, people will put heaters. So the load curve will come. The load curves show the features or some characteristic which we can utilize in our power systems planning. For example, we know that it's a Saturday, so the offices are of commercial places are still on, right? But some of those commercial places will close early, not up until 9 o'clock or not until 7 o'clock. Some might close at 6, some might close at 5, right? That's the thing that we need to remember. Also, we need to remember there are some special days that happens. For example, if it's the Workers' Day, May 1, every year that we observe. So that's a holiday, very special holiday. Workers' Day is a special holiday because the industries even remain in operational on that day because everyone has the right to have that holiday. So that will have a very little demand or consumption of electricity. We don't consume much at our households. We consume the most power in industries. So load curves are very important. So we study that load curve, and from that load curve we can determine the losses because we will know the power from the load curve, and when we know the power, and if we look at the load curve once again, then we will also get the time. So we take the power from the load curve, we take the time from the load curve, then we multiply, we get the energy losses, and then we take the tariff, meaning the rate of energy, and then we get the cost of energy wasted. Then we equate it with the cost of conductor in terms of interest and depreciation, right? Now, as we come to the next bullet point, which is the different types of loads. Now, we need to consider what type of load we are considering in this current situation. Is it an industrial one? Is it a DC load or AC load or DC system or AC system? Or is an agricultural farm that is going to need the conductor that we are designing, and so on. So different types of loads need to be considered in this scenario. Because, like I mentioned just now, that if it is industry, it will have a lot of power consumption, meaning the conductor diameter will be large or larger as compared to if I was considering the line for a domestic connection. Right. So those different types of loads will be considered. And then we come to the next bullet point, which is a load factor. Load factor is the ratio of average load to the maximum demand. Now, what is average load? When we have a load curve, we can determine what is the average load. Even if it is daily load curve, we can see what is the average daily load. So average load can be calculated for any type of load curve, irrespective of their type. For example, daily load curve or monthly load curve or annual load curve. We can find out the daily average load from that load curve. That's why we need to look at that load curve. And maximum demand, meaning the maximum load, we can easily find out from the curve. So those two things, the average load and maximum demand, are available from the load curves to give us the load factor. Now, load factor is important term or terminology that we use for our power systems operation, because this load factor actually gives us very good idea or picture in terms of operation, because that is what all the electrical engineers or power systems engineers look at. This always try to predict what is coming, what can happen now. I need to be prepared, because that's the reason that we are going back, that we cannot store electrical energy. We need to generate it at the time it is being consumed, and at the same time we need to make sure that we operate the system with highest reliability, because it's a large system, it involves energy, so we need to make sure of that. So they want to predict. The load factor tells you what is happening. For example, if I get a load factor of 100%, what does it mean? If I get a load factor of 100%, what does it mean to you? Tell me the answer. If you get a load factor of 100%, what does it mean to you? Think about it and answer, write it down. I'm not getting on any answer yet. If the load factor is 100%, if the load factor is 100%, I calculated the load factor, like I mentioned, we can calculate the load factor from load curves. Load factor is average load over maximum demand. So if I get a load factor of 100%, what does it mean to me? Like I mentioned, that electrical engineers always look at the parameter, and then from those parameters they predict, they understand something, and then they make decision, then they make that decision to be implemented. So it says that your answer is correct. Average load is equal to maximum demand. Yes, that's true when I'm getting 100%. But what does it mean again? What do I understand again when I find that average load is equal to maximum demand? When it can happen that average is equal to maximum? In what situation or what scenario it can happen that the average is equal to maximum demand? No, not for such. It is not the answer. When it can happen?
You are now unmuted.
When the average is equal to maximum. You can't hear me. Current limiting. The conductor is carrying maximum current. Maximum current for how long? Because when we having this load factor, it's related to load curve, and load curve has always a time. If it is a daily load curve, it's 24 hours. If it's a weekly load curve, it's 7 days. If it's a monthly load curve, it has 30 days. An annual load curve, 12 months. Is that clear? So if I say that the conductor is carrying maximum current, it's some words are there, but not 100%. If I consider that we are considering a daily load curve, 24 hours, and we find that the load factor is 100%, and hence we find that the average load is equal to the maximum demand. From that, what I understand or what you understand, what more? During peak usage times, no, that's not the answer. We are considering daily load curve, meaning for 24 hours duration. We're considering the daily load curve for now, for us to understand this picture. Just take a different example. Like you bought 10 sweets, you know those sweets that we eat, and then you have 3 children that you want to give those sweets to. 3 children you have in your neighborhood, you want to give them those 10 sweets. So how you give them? And you finish up all 10. You don't keep any single piece of sweet or more than that with you. You give all those 10 sweets to 3 children. How do you give them? Just give me any number. Right? No. I said you can't give 3.33. There is no 3.33 sweets. You distributing those sweets to them. You can't have 3.33 sweets. You're giving them sweets. Just give me the numbers, how many you are giving to each of them. Children 1, children 2, and children 3. Child 1, sorry, child 1, child 2, and child 3. 10 sweets, 3 children. It's great to think. You're taking months now. You answer, otherwise I cannot continue. Eh? Write down the numbers of sweets given to each of those 3 children. Then you will have 1. If you give 3 to each of them, you will have 1 with you. I don't want that. The 10 you cannot store. It's electricity that we're talking about. You cannot have 1 with you. You have to give 10 that you bought. Each will not help, meaning it will be 9. What will you do with that remaining 1? You can't have extra. In electricity, there is nothing extra. I want to relate it with electricity. You cannot have extra. You cannot have less. It has to be exact same. The demand and consumption and generation. The demand and generation, consumption and generation, they must match all the time. If you bought 10 sweets, you must distribute 10 sweets. Why are you writing 3/3 to each? It doesn't make sense. I said you have 10 sweets, you have to 3 for 3, it makes sense. You're giving 3 to the first child, second child getting 4, and third child is getting 3. So you have bought for 10, you used 10. Now it's analogous to electricity. Now what is the average here? $3.33 is the average. What is the maximum here? 4 is the maximum. So what will be the load factor? Calculate and tell me. Yes, 83%. And it tells me, this 83% tells me that the distribution is such that those numbers are very, very close to each other. There is not much variation. 3, 4, 3. 2 of them are already equal. Only 1 is different. That's why it's close to 100. But if I said that you bought 10 sweets and you have 5 children, how you distribute it to them? 2, 2, 2, 2, 2. Write down those numbers. 2, 2, 2, 2. 5 twos in a row. Write them. You bought 10 sweets and now you have 5 children. Write those that numbers. 2, 2, 2 on the screen. Write them down on the screen so everyone can see. Yes. Now what is the average here? Write down the AVG is equal to, you write down that. Quick, we should not spend much time here. I'm just trying to, yes. Write down what is the maximum value here. Max is equal to 2. So what you see here, average is maximum. Average is equal to maximum. So here the distribution factor or the load factor here is 100%, meaning everyone got the same thing, right? But that is not what I am trying to say. Everyone got the same thing. What I am trying to say, there is no variation. If I consider that 2 megawatt was consumed in hour 1, 2 megawatt was consumed in hour 2, 2 megawatt also was consumed in hour 3, 2 megawatt also was consumed in hour 4, 2 megawatt also was consumed in hour 5, meaning the consumption is not varying. So when the load factor is 100%, the consumption is not varying because average is equal to maximum demand. that is giving us the load factor. So when the consumption is not varying, meaning the consumption is constant all the time for that particular period. If I am considering a daily load curve, meaning for 24 hours, the consumption remains constant, meaning the current will remain constant, meaning the power will remain constant, meaning the energy wastage will remain constant. But as it comes down below 100%, the consumption starts varying, and we'll see these numbers varying. If we get a very low load factor, meaning consumption is varying so much, and for that we will need more and more control, right? So we can determine the average from all those values in the load curve according to hours or according to days or according to months. And when we have powers in the load curve, we can calculate the load current, because if we know the power, we can calculate the current, because we always know at what voltage level that power line is operating. So we can calculate the current, average load current. And from the average load current, we can calculate the RMS current. What is RMS current? It's the root mean square, the value of the current. So what is the relationship between the average current and RMS current that you should have learned in second year or first year? What is the relationship between average current and RMS current, or average value and RMS value of current or voltage? What is the relationship between the average value and RMS value? Do you know about these words, average value, RMS value, maximum value? When you talk about that sine wave, starting from mathematics to electrical engineering, current flow in sine waves, when we talk about alternating current, voltage waveforms, we show the sine waves, peak value or the maximum value is the first one, and then RMS value, then average value. You know those, right? So if we know the maximum value, what will be the average value? Where is the answer? Yes. RMS is not average by root 2. Is RMS average by root 2? Its average value is 0.637 of maximum value. That's what you should say. Is 0.637 is not the correct answer or the appropriate answer rather, because it's 0.637 times the maximum, and RMS is what? I average over root 2 is not correct. Write the correct one quickly. Next, peak by root 2. That's the correct one. So we know how to calculate the RMS value. Now the point is that why do we need that RMS current? What is wrong with average current? We need RMS current to calculate the power loss, hence the energy loss. Why do we need RMS current? What is wrong, or why cannot we use average current? answer if you know it, something, any hints, even if it is wrong, no problem. What could be the reason that we need to use RMS current to calculate
You are now
the
unmuted.
power loss? That I, eh? Eh? Write down it, what you say, so everyone can see.
You are now muted.
Gives us the DC equivalent voltage for the same power. DC equivalent voltage for the same power. It's RMS is related to RMS current. That's what he's saying. Am I right? Okay, let me give you some hints. You will go back and open your books at some point of time today when you have 5 minutes. It doesn't take more than that. So when we talk about average load current, it's related to the amount of charge that is transferred. It's related to amount of charge being transferred in the process. While RMS current is related to amount of heat generated in the process. We're talking about power losses, energy losses, heat generation, and cost of energy. So that is related to heat. That's why you need the RMS current. Is that clear? You will go back to your book. You will find what is the definition of average current. When they talk about average current, they talk about amount of charge transfer, that DC equivalent voltage. If you take average current and put DC, how much is the charge transferred? And if you take AC current and then you find for the same amount of charge to be transferred, how much should be the current in terms of AC? That's the average. So we consider DC and AC equivalents in terms of amount of charge transfer. But when we come to RMS current, we again go for AC and DC, but we don't consider charge transfer anymore. We consider amount of heat generated. So we put DC, how much heat is generated. We put AC, for the same heat to be generated, how much current we need. That current is RMS current. Is it clear now?
You are now unmuted.
In simple words, yes, this relationship to the charge transfer, when we want to find out the DC and AC equivalent or whatever we call it, the average is related to amount of charge transfer. And when we considering RMS current, is related to amount of heat generated.
You are now muted.
So that is why we need that RMS current. So when we have load curve for daily, monthly, annual, weekly, whatever, we can determine the load factor, meaning we know the average value, we know the maximum value, we know the RMS current. When we have that, then we can go for. Now the load curves look like this. This is the daily load curve that I was mentioning earlier several times, from 12 midnight to another 12 midnight, and they vary like that. And this curve looks like smooth, but sometimes if you just putting hourly load curve, there will be just a point here, the point there, point there. There is nothing in between. But because of these days, we have software, we can have a time duration which is very small, meaning we can even plot every minute, and this curve will look like a complete smooth one. And it varies like that. When it varies like that, we see there are some peaks. That word peak you wrote there. There are some peaks here. It goes to a trough, peaks again, another trough, peaks again, and that peak is the highest demand or consumption of the day. that happens at 6 o'clock in the evening or around 6 o'clock, because some offices, industries, commercial places are still on, and people came back home, they started cooking, they put their lights on. Some of them are boiling water to make a cup of tea, someone is having showers, so the geyser is on, someone is watching television. So that's why that peak happens at that time period. And after that, it starts going back, falling. At midnight, it comes to the minimum, because most of the people are sleeping, and the minimum load demand that you see there, it cannot be going to zero, because many industries operate all day, 24 hours. So that is the industrial load. Some railway traction also consume electrical energy for their motors they use for traction. So that's the contribution there that comes as the minimum one. It can't be going down to zero. And what does it mean to us as power system operators or engineers or technicians? That you need to be prepared to match these demands. Like you can't have bought 10 suites and giving 333, keeping one with you. It's not possible. So you have to match all these demands. So you have to predict what is coming at 6 o'clock. Is it 6 megawatt or 60 megawatt? So you prepare accordingly, and then make sure that when that time comes, you are capable of supplying that power demanded by different types of consumers to meet the economy requirements. Otherwise, people will complain, it is load shedding. So that's that one. And this is a daily load curve. We can plot a weekly load curve, we can plot monthly load curve, we can plot annual load curve. The features are same. And from these load curves, not only when we just talk about how can we meet the demands, for example, you are running a coal-fired power station, or you're running a diesel engine power station. So you need to know, if I have to meet this 6 megawatt demand in the evening, I have a diesel engine power station, I need to make sure that enough diesel is there. If I don't have, then I should have ordered it 2 days ago, because they need that 2 days to supply that amount of diesel that I will need in the evening 6 o'clock. So that's another part of planning, daily planning. Right, so we can go to the next one. But if you have any question in relation to this load curve, you can ask. A lot of things that we do from these load curves. Any question from here? Okay, it's fine. Let's go to the next one. Now, as I mentioned that we calculate the load factor from the load curve, and then we see the average load, we see the maximum demand, we can get the RMS value. And there are some tables that we used in olden days, but nowadays we use the load curve straight away. It was, if the load factor was 10 to 100, how it's varying from 10 to 100%, is something now related to the form factor. Now, form factor is what? You hear anything like that, form factor? What is a form factor? What is a form factor? So what is the form factor? When we talked about average value, maximum value, RMS value, then we knew that load factor was average by maximum demand. So what is form factor? Did you hear that word, this word before? No, you didn't hear. So the form factor is coming from those words.
Now muted.
RMS value, average value. So form factor is the ratio of RMS value to the average value. Form factor is related to RMS value and average value. So if we get a pure sine wave that we talked about earlier, that average value is 0.637 times the maximum value, RMS value is going to be 0.707 times the maximum value. What will be the form factor of a pure sine wave? The form factor is the ratio of RMS to the average. Calculate and tell me. What will be the form factor? If we have a pure sine wave, what is the answer? It doesn't take more than 10 seconds. Are you still there?
You are now unmuted.
I have not seen any answer. What is the value of form factor if you have a pure sine wave? Form factor is the ratio of RMS value to average value. What is happening? You don't have calculator. Use the one in your phone. Write down the answer, please. No answer yet. This is a first year, second year thing. You must write 1.11. Yes. If you did not know, you must calculate it. It's the ratio of RMS value to the average value. We know the RMS value from this equation, maximum over root 2, and we know the average value 0.63 times, 637 times maximum value. Now we can see that RMS value and average value, they give this factor which is called form factor. Now that is also somehow related to load factor, because load factor has that average and maximum demand. It doesn't have the average load and maximum demand is giving us the load factor. So they are related. So this table shows how the load factor and form factor are related. We don't use them these days anymore, but in olden days they were used. But the reason why they were used is that from this form factor we come to something called loss factor, which you did in here. I will explain that one. Now the loss factor is coming in terms of a ratio. It says it's the ratio of actual energy loss to the energy loss, assuming that maximum current is flowing over a period of time. So loss factor is expressed as the ratio of actual energy loss to the energy loss, assuming that maximum current is flowing through the line over a given period of time. And when we're talking about Kelvin's economy law or Kelvin's law, it's the time is a year, 8,760 hours. So actual energy loss that is taking place in the line, meaning because of current flow, and if the load factor is 100%, these two will be the same. But if they are not, then it will be less and less. So for that, they have given us some empirical relationships here for the loss factor and load factor. That capital F that you see here is the load factor. How load factor determines the loss factor. So for example, it can be 0.2 times F plus 0.8 times F squared, 0.3F, 0.7F squared, 0.5F, 0.5F. So loss factor and load factor, they are related by this empirical formula. So we will do some tutorial in which we can have this type of expression giving the relationship between the loss factor and load factor. And this also gives us a scenario like I was trying to explain when looking at the load factor of 100%. If the loss factor is 100%, we can see the actual energy loss, and this energy loss, assuming the maximum current flow in the line for that given period of time, will be the same. Now I'm coming to the graphical representation of, okay, I'm sorry that I didn't give you a break, because you have already had a break in the beginning of 10 minutes or so, but I didn't have, but it's okay. We'll finish around 12 or so, then you can have your little longer break. Now, we saw in the beginning that when we are talking about Kelvin's economy law in terms of giving us total minimum cost incurred in terms of the conductor cost and the cost that we come to deal with the energy cost or cost of energy in the line. So it gave us that cost of conductor should be equal to the cost of energy wasted in the conductor annually, meaning C1 should be equal to C2. And we also found that the total annual cost should be the minimum. That was the condition, and from that we found those conditions. Now if we try to plot them, like if you remember that they were the total cost C, capital C, and if we divided that into two costs, C1 was the fixed cost, standing cost, and then the C2 was the running cost. Fixed cost came from the conductor cost, running cost came from the cost of energy wasted in the line in the conductor. Now there where C1 fixed cost was directly proportional to the conductor cost, and hence the cross-sectional area of the conductor, meaning C1 was equal to K1 times A. And when it came to the running cost, the cost of energy wasted in the line, we found that cost of energy wasted in the line is inversely proportional to the cross-sectional area of the conductor, meaning it was K2 over A. Now if we take those two equations, K1 times A and K2 over A for C1 and C2, so we put cross-sectional area here on the x-axis and total annual cost and other cost, fixed cost, running cost on the graph. I drew it using MATLAB. So cross-sectional area, if it varies from 0 to 1 unit, for example, it can be meter squared. How the fixed cost will change? The fixed cost will remain in a line all the time because it's directly proportional. So as you increase the cross-sectional area, the conductor cost increases, the fixed charge increases linearly. But if you increase the conductor cross-sectional area, what will happen? Running cost will decrease. So if the conductor cross-sectional area is small, the cost is high. And as you increase the cross-sectional area, it's hyperbolic curve, and it goes down, 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 down. But it doesn't decrease to 0. It won't, because it will have some loss all the time. So these are the two costs, fixed cost and running cost. The blue one and the green one is the running cost. Now what we said, the total cost will be the summation of these two costs, fixed cost and running cost. So if we add them, okay, if we add them, can we do it just after 10 minutes? Oh, you just taking it. Oh, yes. So if we add those two costs, fixed cost and running cost, we get the total cost C, which is the red curve. So it looks like this now. And the lowest point on that curve C provides us the total annual cost. And the point corresponding to that cost on the cross-sectional area line is the most economic cross-sectional area. So OM, if we say that, is the cross-sectional area is most economical one. So we can plot the cost considering the cross-sectional area and find out it graphically as well. We don't necessarily need to do it analytically using the equation. If we can use those equations, And for them, we can find out the different costs involved in the process, and then find out the economic cross-sectional area as well from the graph. Is that clear?
You are now unmuted.
Say yes or no. Okay, that's fine. Okay, let me stop it here, because now the next slide is coming with limitations of Kelvin's law. It has a lot to discuss. So if you have any question, you can ask. Otherwise, we can conclude today's session. But I have some questions for you. I'm not sure if you did that, what I asked you the other day. I didn't forget. I asked you to collect all the ratings of those appliances that people normally use at their households, starting from electric bulbs, kettles, microwave, refrigerator, geyser, television, guitar, hair dryer, and so on. Did you do that? Anyone? Has anyone done that? Has anyone done that power rating of the appliances at, in our houses? I'm saying last time I asked you to go and check on internet or anywhere for the power ratings of the appliances that we use in our houses or households, homes, whatever you call it. Did you do that, anyone? Okay, so what is the maximum power rating of the appliance, or what is the appliance that has the highest power rating? Is the appliance that has the highest power rating in our homes? Which appliance is it? Refrigerator, or is it a stove, electric stove, or a geyser, or a television? Which one consumes the maximum power? Microwave and geyser. How much is the power consumption there? What 3000 watt, right? 3000 watt. But again, like I mentioned on day one, that whenever we get some answer, it's an answer we have arrived at, but it does not necessarily mean that we have to stop there. So when we look at the microwave and the geyser, we still need to think a little more in terms of what? In terms of time of operation. For how long we use microwave, and for how long we use a geyser, even if their power ratings are the same. Let's say we have a microwave of 3000 watt and also a geyser of 3000 watt. For how long we use when we use a microwave, for how long we use when we use a geyser? Are the same? Yeah, for the whole day, because most of the times we use it in terms of minutes. Sometimes we use just warm up, maybe 1 minute or less than a minute. But if we want to keep our geysers off all the time to save our electricity bill and hence the energy for the supplier, that's what ESCOM puts on the television, put your lights off. So if we switch off our geyser and then this is a cold morning, I need to have a warm shower, how long it will take to get the warm enough water for me to have a shower? No, not an hour. It should be about 20 minutes to half an hour. So that consumes a lot of power, a lot of energy. Can you imagine now? 3000 watt microwave in 1 minute, 3000 watt geyser half an hour. So that now goes back to the power system engineers. They need to supply that 3000 watt for 1 minute for microwave on, 3000 watt for half an hour. In the morning time, some people used to shower. In the evening time when they come back home from their works. That is also a planning part. So those only wattage, if we look at the wattage and if we are not aware of the usage of those appliances, we cannot plan well as an power systems engineer or electrical engineer. Right. So in everything there is more. Right. So the other day I asked you a question, if you remember that when I asked you that 400 volt, and then there's this picture of a skeleton and bones and all those stuff, the danger sign. If you remember that. So what was also not mentioned there? It's an AC that we talked about, 400 volt, 3-phase, star connection, neutral. We talked about what else we can also know from that simple sign as electrical power system students and hence electrical engineer that we want to be. What else we could expect there? A little more, that when it's 3-phase AC, star connection, neutral, we need to have a single phase loading. Single phase appliances are there, like our kettles, refrigerator, all those are single phases. So what else is missing, or what else we can understand from there? You mentioned that if we connected, I remember that I said we got the voltage 240 between phase A and neutral, got the voltage of 240 between phase B and neutral. For phase C and neutral, we also said that it will be 240. Do we remember that? Do we remember, everyone? Say yes or no. Okay. If we remember that, and if we now in real life we go and measure, will we get 240 for phase A and neutral, for B and neutral, C and neutral? What do you expect? Will you get 240 everywhere? Same value, 240.0, 240.0, and 240.0. What do you think you will get in real life? 230, 220, and the other one? T values we're talking about between A and neutral, B and neutral, C and neutral. What you said, you gave me two values, 230, 220. The third one, I'm assuming that it was between A and neutral, 230, B and neutral, 220, C and neutral. What voltage you expect? What voltage? Not sure. Any value, you just say any value. I always used to say, don't worry if it is wrong. Because if you say something wrong, then we can learn from that one as well. Why it is wrong, how wrong it is, too much wrong, or is it just acceptable, it's a little wrong. So give me a value. Two 230 we have 220, and we said it should be 240. Huh? How much? 210. Hello? 210 is fine. So we have 230, 220, and 210. Why are you expecting it to be different like this? 230, 200. 20, 210. Why are you expecting it to be different like this? Because our calculated value was 240. Why are we expecting it to be different? None of them are same. Even if it was 230, 230, 230, we could have a different explanation. If it was 220, 220, 220, we could have a different explanation. So now it's not that two things have happened. It has come down from 240 and below to some other values, and they are all different. Is it not right what I'm saying? That two things have happened. It was supposed to be 240, that's what we said, and then was it 240? I can't remember correctly. How much was it? No, it was 230. So if we consider 400 volt in the first place, then it should be 230. If we consider 4.5, okay, you said it was if it was 230, yeah, it was 230. It was supposed to be 230 for all the phases. Now they are different. 230, 220, and 210. Why are they different? Okay. What loss? Because of phase angle and voltage drop loss. Because of phase angle and voltage drop loss. Somehow correct, but we need more explanation. What do you mean by phase angle and voltage drop loss? So I'm keeping this question to you. Think about it today and explain it. What is happening to voltage drop loss and what is happening to phase angle? Why these two are coming into the discussion now? Is that okay? We'll discuss about that at some point of time. Yeah, thank you. You have any question? Okay, it's fine. Then we can conclude it today. We'll continue tomorrow in the morning. Thank you very much.